Welcome to the Explainer. So, I want you to picture this. You're right in the middle of a high-pressure data engineering interview. You've cruised through the initial screening, you're sitting across from a senior engineer, and honestly, you're feeling pretty confident. You know your way around PySpark, you know how to optimize queries, and you definitely know the golden rule, right? If you're going to use a dataset multiple times, you cache it. Simple. But then the interviewer leans forward and drops a scenario on you that completely seems to break that very rule. They hit you with this exact, notoriously tricky prompt. You cached a data frame, but the second action is still slow. Why? Now, at first glance, this sounds like a total paradox. I mean, the whole point of caching in Spark is to make repeated operations faster by keeping the data right there, ready to go. So why on earth would Spark still take a long time to process it? Well, this question isn't just a cheap trick. It's specifically designed to expose whether you actually understand Spark's backend mechanics or if you're just, blindly memorizing commands. Today, we're going to solve this paradox step by step and arm you with the ultimate technical answer so you can absolutely crush that interview. Okay, let's dive right in. To solve this mystery, we really have to start with one foundational concept, and that is Spark is lazy. And honestly, in the world of big data, that laziness is a massive feature, not a bug. When you write a line of code calling the cache function, Spark doesn't just instantly spring into action and shove your data frame into memory. Instead, it kind of just takes a mental note. Think of it like a restaurant order. Writing it down on the ticket doesn't mean the food is cooked. It just marks that data frame as eligible to be cached. Literally, the cache isn't populated until an action actually computes the relevant partitions. And that brings us straight to reason one. The cache was never fully materialized. You see, calling an action doesn't just magically guarantee that your entire dataset is now resting comfortably in memory. It entirely depends on what specific action you called to trigger that initial computation. Let's actually de-jargonize this whole materialization thing by contrasting two super common actions. A lot of engineers will run a quick show command to check their data, right? And they just assume the data frame is now fully cached. But here's the catch. A show command typically needs only enough data to display the requested rows, so it may compute and cache only a subset of the partitions, rather than the entire data frame. Spark is highly optimized to save time, so it knows it doesn't need to scan a massive dataset just to show you a tiny sample. That means only a few partitions may actually make it into the cache. Contrast that with count, which forces Spark to compute the entire data frame, and therefore gives Spark the opportunity to cache all of its partitions as they are computed. So if your first action was just a show, and your second action requires the whole dataset, well, Spark has to go all the way back and compute all those remaining uncached partitions from scratch. The result? Your second action drags because it's doing all the heavy lifting you thought was already finished. Which naturally leads us to reason two. The data frame simply doesn't fit in memory. This one comes down to the inescapable physical limits of the hardware running your clusters. Imagine you've got a massive 100-gigabyte data frame. You trigger an action to cache it, but let's say your cluster has 5 executors, each with a 16-gigabyte memory limit. That's 80 gigabytes of total cluster memory. The intuition is correct, but this isn't a precise calculation of how much data Spark can cache, because executor memory is shared between execution, storage, overhead, and other workloads. And the in-memory representation of the data frame may be very different from its source size. So 100 gigabytes of source data does not necessarily mean 100 gigabytes of cache memory is required. And because the available storage memory may be insufficient for all cached partitions, Spark can evict older cached partitions to make room for new ones. It literally tosses them out to make space. Later on, when your second action comes along and asks for those specific partitions, they're just gone. Spark suffers what's known as a cache miss. It reaches into its pocket for the data, realizes it's empty, and to recover, it has absolutely no choice but to completely recompute those missing partitions from the original source data. So even though you explicitly use the cache command, you are still paying full price for those expensive computations. Now, moving on to reason 3, the cache uses disk because of the chosen storage level. This is essentially Spark's backup plan for when the available memory isn't enough, if you've selected a storage level such as memory and disk. Depending on your storage level configuration, Spark can keep partitions that don't fit in memory on disk instead of recomputing them later. But here's the crucial point. You have to understand the physical limits at play here. Reading data from RAM is lightning fast. It's like grabbing a document right off the top of your desk. That's exactly why we cache in the first place. But reading data from disk is generally slower than reading it from memory, although the actual performance depends heavily on whether you're using local SSDs, network-attached storage, cloud storage, and other infrastructure. It's kind of like having to walk down the hall, unlock a heavy filing cabinet, and manually flip through folders. So yes, using a disk-backed cache can prevent recomputation, but it can still make the second action slower than a fully memory-resident cache. And one important terminology point, this is different from Spark's spill to disk during execution. A cached partition stored with memory and disk is not the same thing as shuffle or aggregation data spilling because execution memory is insufficient. Next up, we uncover the fourth puzzle piece. Reason 4, new expensive downstream operations. You see, even if your data frame is perfectly and entirely cached in lightning-fast RAM, you still have to look at what that second action is actually asking Spark to do. A cached data frame doesn't just magically make your brand new transformations free. For instance, let's say your second action involves a group by command. Will Spark use the cached data? Yes. Will the query still be incredibly expensive? Also yes. Why? Well, because operations like group by, many data joins, complex aggregations, and sorting can require a shuffle. During a shuffle, Spark has to physically redistribute massive amounts of data across the network to different executors. This means data is literally leaving the CPU, traveling through the cluster network, and being serialized and deserialized. This network communication, sorting, and physical data movement can be heavily expensive and slow. And here's an important nuance. Not every join or sort necessarily causes a large shuffle. For example, Spark may use a broadcast join when one side is sufficiently small, avoiding a large shuffle of that side. Caching only saves you from rebuilding the starting line, right? It does absolutely nothing to eliminate the heavy lifting of the race itself. And finally, we've reached reason 5. Spark may not be getting the cache benefit you expected. Now, this is perhaps the most frustrating reality to uncover, but it happens for several legitimate reasons. An executor storing your cached partitions might have suddenly failed or crashed. Those lost cached partitions can be recomputed when needed. The memory might have been cleared manually through something like unpersist command, or cached blocks may have been evicted because of memory pressure. Also, don't think of Catalyst as randomly ignoring your cache because it found another plan it likes better. When Spark recognizes a cached logical plan or subplan, the optimized plan can contain an in-memory relation, and the physical plan can contain an in-memory table scan. However, if your second query doesn't actually reference the cached data frame or its matching logical plan, Spark may legitimately read from the original source instead. So how do you catch Spark in the act? Well, as an engineer, you don't just guess, you verify. You run the explain command on your data frame to view the physical execution plan. And you want to hunt for specific keywords here. If you see in-memory table scan, congratulations. That indicates Spark is reading from the cached representation for that part of the plan. But if you look at the plan and see something like file scan, it means that part of the plan is reading directly from the underlying file source rather than the cached representation. However, seeing a file scan doesn't automatically mean Spark ignored the cache. Your query may legitimately contain multiple inputs, and only the portion corresponding to the cached data frame may use in-memory table scan. Knowing how to read this physical plan is an absolute superpower in a technical interview because it proves you actually know how to debug under the hood. All right, so we've broken down the 5 main culprits. How do we tie this all together when you're actually sitting across from that interviewer? You want to deliver an authoritative, comprehensive response that proves you deeply understand the internals of Spark. Take a breath, and when they ask why the second action is still slow, you confidently say, "Caching is lazy." Calling cache command alone doesn't immediately compute or populate the cache. The cache is populated when an action computes the relevant partitions. Even after that, the second action may still be slow if only part of the data frame was cached. Cached partitions were evicted, the cache is disk-backed, the data had insufficient storage memory. The second action performs expensive operations, such as shuffles, or the query isn't actually using the cached representation. I would verify this using df.explain command and look for in-memory table scan in the physical plan. Boom. Memorize that. You have just demonstrated absolute mastery over lazy execution, memory management, and query internals. Mastering the nuances of caching will absolutely elevate you from a beginner to an expert in the eyes of literally any engineering team. But as we've seen today, caching is really just the beginning of the story. If Spark can hide so much complexity behind a single, simple command, it begs the question, what other PySpark secrets and performance bottlenecks are currently hiding inside your execution plans? Keep exploring, keep questioning, and I'll see you in the next explainer.